I'm Purushottaman, student of Computer Science Engineering Department, Sri Venkateswara College of Engineering. Today I'm going to present about the project AI-driven Zero Trust as a Service platform for cloud native application. So, cloud native applications increasingly rely on distributed architectures and exposed APIs, and these are making access control a critical security concern. The traditional systems are mostly based on RBAC, which is role-based access control mechanisms, which only establishes trust at the login and fail to establish trust after post authentication. That is, when a user after login, he cannot. The continuous monitoring is actually being missed. So the project brings out the objective of zero trust security, which addresses these limitations by enforcing continuous verification of identity, device, and access requests. And moreover, modern cloud environments require application independent and dynamically scalable security solutions capable of adapting to evolving threats in real time. So the problem statement of the project is actually modern cloud application mostly rely on static authentication and role-based access control. So in order to reduce the post authentication attacks and continuous evaluation of the user behavior and trust, uh, this we propose a solution of zero trust as a security as a service, which is totally application independent and which could be plugged into any application by configuring to the application's backend system, which is based on this. And the system is completely adaptive to the whatever application we are going to plug in with. So going on with the abstract of the problem of the project, the project implements an AI-driven zero trust API gateway that centralizes authentication, authorization, and continuous user monitoring. The gateway verifies whether client tokens enforces role-based policies and issues short-lived internal JWTs for secure back-end communication, eliminating implicit trust between services. To enhance security, the system integrates machine learning-based risk engine that continuously analyzes user behavior such as request patterns, locations, and access frequency. Based on real-time scores, the gateway dynamically adapts access decision by reducing privileges, shortening token lifetime, or blocking suspicious activity. The solution demonstrates how zero trust principle combined with adaptive intelligence and can provide scalable and modern cloud native access control. So the proposed work includes the design of AI-driven zero trust security as service platform to secure cloud native application without modifying application code. Implement a zero trust gateway that is a reverse proxy to intercept all the user and API requests and enforce centralized access control. Integrate with OAuth 2.0 or OpenID Connect identity providers for authentication while retaining independent authorization control. Develop a continuous trust evaluation engine to assess post-authentication user and session behavior in real time. Employ a machine learning-based anomaly detection system, isolation forest model primarily, to detect abnormal access patterns and compute a dynamic trust score. Design rule-based policy as code enforcement engine, where administration define access policies using role, resource, and trust score thresholds. So this is the architecture of the entire project. So we have majorly three layers in this gateway. One is the authentication and session management layer. Second layer is the trust evaluation layer, and third layer is the policy control and enforcement layer. Whenever a user or API client hits the backend respective cloud native application, our gateway acts as a reverse proxy, which intercepts all the APIs which reaches out the cloud native application. So the zero trust gateway actually what does is it takes the request first. It needs to validate the token. So the gateway initially provides an internal JWT token which encapsulates the actual JWT of the cloud application. So based on that, the JWT is actually verified and the authentication is provided by the first layer. And if the user is authenticated and if it is a legitimate user, the trust evaluation layer starts working. It actually takes all the uh, metadata, telemetry data from the user request, such as the HTTP method, the request time, the number of requests per minute, the status code, which is whether it is success or failure, and several other things, several other metadata of the request, and it segregates them as a um, log file or telemetry logs, and then extract the features from the telemetry logs, such as the total request or a period total request per minute, what is the failure rate, what is the success rate for per minute, etc. And from that, we actually provide two different trust scores. One is ML based trust score, and other is actually rule based trust score. A rule based trust score work by providing trust score based on the uh, statistical methods like standard performing standard deviations, Z score, etc. So the system actually learns to adapt with the baseline. First, it collects all the request data, metadata, telemetry logs, and every 1 hour it draws a baseline data from whatever the data telemetry log collected for every 1 hour. So based on that, the baseline keeps getting adapted to the system. So when a new request comes, the request telemetry data are extracted and it is converted to the features, and which is compared to the uh, baseline data which we have already drawn. And based on the statistical comparisons, performing standard deviations, Z score index, and several other things, we derive at a score of trust score based on the rule based system. Then we use we run the ML service as a separate microservice. So we send the meta feature data to the ML model through queue. We publish the data in the queue. The queue would actually deliver the all the feature data to the ML model. The ML model gets trained based on the previous risk score and the telemetry logs which have been stored in the MongoDB. And after that, based on the trained data set, ML actually predicts the trust score and the risk score of the risk score of the system. We actually use isolation forest for the isolation forest model for this system. So after performing ML trust score, we the score is get stored in the database MongoDB. From there, our gateway actually collects the data, and it takes the 50% weightage from the rule base and 50% weightage from the ML base, and combine it and provide the data to the provide a risk score. Based on the risk score, the user may be authenticating allowed, or the user may be rejected. So based on the risk score, we categorize the user as a normal user, suspect, and attacker. If it is a normal user, is allowed to pass through the gateway. If he's not a normal user, it's a suspect, means he requires a post authentication. And again, and if it is attacker, it is suspected as it is confirmed as attacker, means you completely block the request, and the request would not be allowed. So after passing through the trust evaluation layer, the user would maybe need to uh, the request would be passed through the control and enforcement layer, where the admin defined policies for the application, like the role-based access control, and several authorization policies defined would be checked, and if it matched, and if the request is authorized, means we would be passing through a backend application. So or else we would not pass the request to the backend application. This is the overall architecture of the system. So we may think that this three layers would cause an high latency latency to reach out the application, but it is not. After a lot of efficient approaches, we bring up the system to be or the latency to be around less than 100 milliseconds. Most probably it takes 20 to 30 milliseconds to on an average. So we can give a maximum threshold to 100 milliseconds. Before that, the overall latency of the gateway lies down. So the system requirement for this is just an Intel i5 processor, 8 GB of minimum required RAM and storage of 20 to 30 GB of free disk stored, and a stable internet connection. And let's dive into the implementation part. So here now we are running the code actually. So the system is being already uh, in run. So for the demonstrative purposes, I have created a demo script which runs the system. So one second. Okay, this is the basically the UI of the system. So we have actually have a login page where we get to log in, and in the dashboard you would see the analytics of it. So when I hit the demo simulator, it get the analytics here. So if we refresh here, we get to know about the data. So 1% anomaly request has been came, and 99% of them are normal requests, and for the total request we got, everything will be stored here. And in the auth policies, we can set the authentication roles. Right now, I have simulated a backend system and which is running in 3000, where we have defined three different endpoints, and we have defined the authorization policies for it. And then here is the risk policy where we can set the risk threshold for the various risk category. And then here is the system config where here is where the backend system is actually working. We can set to it as an enforce mode or observe mode. Observer mode will not block any user based on the risk level. It just observe logs and log all the activity of the user. In enforce mode, we get to know about after performing the risk score, we actually block the user based on the risk level. And here we get to know about the telemetry data. So if we yeah if we get to know about if you want know the log of particular user, means you can search out the user, and based on that we get the user's activity, like what are the endpoints have been accessed, the status code or authorization which is allowed or not, etc. And here is what I told about the baseline. Our system draws the baseline every 1 hour. Based on that, we actually compare with these are the features actually I told, feature extracted features. Based on this only, we perform the statistical risk score, and that's it. So overall, the system provides an continuous evaluation and engine which is completely decoupled and independent from any application, so which can be plugging with any of the application easily, and it ensures the security and continuous monitoring and assessment of the system. So thank you everyone for watching. So that's it. Thank you everyone.